Welcome again, students. We will look at some of the topics that we have covered in the last session and then bring in to introduce some new topics. So let us look at just a quick glance at what we have looked at in the last session. We looked at discrete time signals and their properties. We looked at the definition of what constitutes a linear system and a time invariant system, and then when you have the two together, a linear time invariant system, how it is represented by means of the impulse response or the unit sample response, and for an LTI system, how you can get the output for any input by means of the convolution, which is using the unit sample response. So this is what we have covered. We have completed up to section 2.4. Actually, we have already covered 2.4. You can take a look at that as well. In terms of the topics, you can see that almost everything is ticked except for Bibo stability, which we will be covering today. So here is a quick description of how to do convolution using the analytical method. Analytical method means using the formulae. Analytical method. So again, very simple, but I want you must be very careful in not making a mistake, because you must apply the concepts very, very carefully. So here again, let's look at a sequence, interesting sequence where this is an example. We'll look at two examples. This is the first example. X of n is equal to a power n u of n. We are given that a is a real number which lies between 0 and 1. So therefore, this is a decaying exponential. It's an infinitely long sequence, a causal sequence. We are told, like in the previous case, that this is also equal to h of n. X of n equal to h of n. Very good. Anyway, what we are interested in is y of n equal to x of n convolved with h of n. The formula for this is summation k equal to minus infinity to infinity. X of k, take the input, keep it as is, take the impulse response, time reverse it, h of n minus k, and then do a point by point summation. Okay, this is what we have. Now, step 1, substitute for x of k. Substitute for x of k. Okay, now take this summation k equal to minus infinity to infinity. X of k will be given by a power k u of k. Okay, don't get confused between n and k. What is the argument is k. If you have argument of k, it will be a raised to the power of argument u of the argument. So a of k u of k times h of n minus k. Okay. Now your summation in the general case went from minus infinity to infinity. Now, but tell me, look at your the summand, the term that is inside the summation. Where is it non-zero? When you multiply it by u of k, it will make the summand 0 for all negative values of k. So taking these two into a common, looking at these two, then it says that the summation can now be written as k equal to 0 through infinity, because u of k is non-zero only in that range, 0 through infinity. So 0 through k, now I don't need to write u of k anymore, a of k h of n minus k. Very important step, let me repeat it. The original expression for the summation goes from minus infinity to infinity. But when you look at what terms you are summing over, these terms are 0 for k negative values, because the input is not defined. So basically this product will be 0 for all k less than 0. So therefore this summation becomes summation from 0 to infinity. So next step, step 2. Okay, so this is step 1, step 2. Step 2, substitute for h of n. Substitute for h of n. Okay, so let us see what is the expression. H of n equal to a power n u of n, same as the input, but what we need is h of n minus k. So, h of n minus k will be a of n minus k u of n minus k, u of n minus k. So, let us substitute here. So, y of n is equal to summation k equal to 0, because we already have changed the lower limit. Now, upper limit goes up to infinity. I get a power k, a power n minus a power n minus k. Okay, you can see how a power k and a power minus k will get changed. But let us see how we can simplify this expression further. Okay, and basically we say that this will be u of n minus k, u of n minus k. Now, where is u of n minus k non-zero? This is non-zero everywhere where the argument is positive. Okay, non-zero if n minus k greater than or equal to 0, okay, which is, if you simplify this is nothing but k, take it to the other side, is less than or equal to n. This is the only place where the u of n minus k is non-zero. So, that means k cannot go into all the way to infinity, because there will be a lot of zero valued terms. Combine these two together, the upper limit and this u of n minus k, and then you will find that the upper limit can, you can go to infinity, but many of them are zero valued terms. So, till where will you get non-zero terms? Only until you go to the value of n. Okay, so this is equal to summation k equal to 0 through n. Upper limit is n. A of k, a of n minus k. So, if you simplify, this comes out to be a of n, and a of n is doesn't depend on k. So, what we can do is you can remove a of n outside, you get k equal to 0 through n, and this you can leave it as a constant equal to 1. Okay. So, which means when you add this term, you will get 1 plus 1 plus 1 n times. So, this is nothing but a power n times n plus 1, or n plus 1 times a power n. Okay. And remember, can you get negative values of this expression? Can n be negative? No, because if you look at both are decaying exponentials, you flip one of them and then you move it to on the negative side, you will see that there is no overlap. So, this expression is valid only for positive values of n, which means you have to write it as u of n. Okay, so any negative values you can. So, for this particular example, the output y of n is given by n plus 1 a power n u of n. Okay, now you may say, well, you know what, I could have done it graphically. That is correct, that's a very valid point. But what if I asked you, give me y of 32? Now, that would be very difficult for you to sit and do the calculation. But if you had this analytical method, then you would say this is equal to 33, n plus 1 is 33, a power 32, right? That is what it will be. So, you can write down for any arbitrary output, you can write down the expression once you know the analytical form for the convolution, and this is the advantage again. So, you should be able to do convolution graphically. You should also be able to do the convolution using the analytical methods, and we will even in the next few sessions and also in the practice sessions, we will give you a number of exercises which will help you practice both the graphical method and this method. Now, along the same lines, I would like you to try out a homework, something that I would like you to try out. Again, you can look at this example as a reference and you should be able to do this. Okay, we are given an LTI system whose impulse response h of n is equal to a power n u of n minus 1, and we are given a greater than 0 less than 1. So, it will be a decaying exponential, but it will start at n minus 1, as n equal to 1, right? That's how we understand that. So, basically you are taking this exponential and then you have u of n minus 1. So, what will be the first non-zero sample? So, if you look at h of 0 is 0, h of 1 is equal to a, because u of n minus 1 will be, then h of 2 will be equal to a squared and so on. So, basically you have a decaying exponential. It does not start at 1, but it starts at a, you will get a squared and so on. Okay, I hope you are comfortable with that. Now, we are given that the input x of n is the unit step function, but also delayed by 1 unit of time, u of n minus 1. So, let us look at what is this expression. This input basically says this is equal to 1 if n is greater than or equal to 1, okay, or 0 otherwise. Okay, this is the expression for this. And by the way, we can write down an expression for this one also. This is equal to a power n, h of n is equal to a power n if n greater than or equal to 1, equal to 0 otherwise. Okay, so this can be captured using this expression. Okay, this is what is coming. So, now I want you to look at the convolution y of n is equal to summation k equal to minus infinity to infinity x of k h of n minus k. Okay, and we do not need to do it one step at a time. We can do a substitute for both. Summation k equal to minus infinity to infinity. What is x of k? What is x of k? X of k will be u of k minus 1. That will be the expression, because x of n is u of n minus 1. This is u of k minus 1. The next term is a power n minus k u of n minus k minus 1. Please make sure you are getting exactly the correct expressions, because if you get the expressions slightly differently, then it will be a problem. Now, this term can also be written as u of n minus 1 minus k. Again, it's just basically reordering the terms. So, now look at the combination of these two and tell me what will be the lower sum, where will your summation start from, and look at the other two terms, numerator, instead of going up to infinity. If you look at the expression for u of n minus k, you can modify the upper limit. Okay, what I will do is just give you the limits and then ask you to come. So, what I want you to do is two things. One is verify that your lower limit is k equal to 1, verify that your upper limit is n minus 1, and then get the expressions. And so, this is to be completed. That is the homework. Okay, and make sure that you are absolutely comfortable changing the limits, also what to write down in terms of the expression within the summation, and then final expression. We will look at it and write it down once we when we meet next time. But definitely want you to try this out so that you will get a clear understanding of what the expressions are. All right, so now we can move forward, because we have looked at a few examples, and then we are able to have a good understanding of the process of convolution, and I think this is very very helpful. Maybe this is a time for us to look at a recap of some of the key concepts that we have studied so far. So this is another example. Okay, this is a combination of concepts example, combination of things that you have studied, and so you will have to apply multiple rules that you have obtained. Okay, x of n is equal to 1 minus summation k equal to 3 to infinity delta of n minus 1 minus k. Okay. We are asked to write this signal in the form of the unit step function, which has a scaling mn minus n naught. Okay. There is a shift and then there is a scaling. Okay, we are asked to, so we want to, so if this is x of n, what is m, what is n naught? Okay, and the easiest way that you can verify this, look at a sketch of the input sequence. X of n is equal to 1. What is 1? If it is equal to 1, that means it has all samples equal to 1, from minus infinity to infinity. Okay, that's what the first one does. So this is 0, 1, 2 on this side, minus 1, minus 2 on this side, on both sides. This is x of n equal to 1. Now from this, we are going to subtract some number of inputs. It starts with k equal to 3. So if you substitute k equal to 3, you get delta of n minus 1 minus 3, which is the same as n minus 1 minus 4. So delta of n minus 4, what is that? This is a unit impulse which is sitting at n equal to 4. So if this is 3 and this is 4, there is a unit sample sitting at n equal to 4. When you subtract, this will cancel this. Then the next term is n minus 5. Okay, there is a sample sitting at n equal to 5. You have a sample here. This will cancel with this. So if I have a sample here, no, I want a green sample. Okay, green sample, that will be cancelled by here and here when I do the subtraction. So this is delta of n minus 5. Okay, this is delta of n minus 5. And if you go on doing this, you will find that the resultant that you get is a sequence which looks like this. It has got a value equal to 1. Okay, and it has on the positive side, this is 0. It has a value, this value equal to 1 for n equal to 1, n equal to 2, and for n equal to 3. After that, these delta functions will knock off, so therefore you will get 0 valued samples here. Okay. Now, does this look like a unit step? That's an important question. The answer is yes, it looks like a unit step, but it is not going towards the right, but is going towards the left. No problem. All you need to do is time reverse the unit step, and is it starting at n equal to 0? No, it is starting at a different value n equal to. So if you want the unit step to be non-zero up to when you time reverse up to 3, then what we need to do is get an intermediate signal x1 of n equal to u of n plus 3. Okay, you have n plus 3, that means you have advanced it up to, starts at n equal to minus 3, and then if I time reverse it, y of n equal to x1 of minus n, if you time reverse this sequence, you will find that this is equal to u of minus n plus 3. Okay, u of minus n plus 3. You sketch this one, okay, sketch this one and confirm that this one is exactly the same as what we have represented. So we have the following: x of n is the expression that we have here, 1 minus summation k equal to 3 to infinity delta of n minus 1 minus k. We have been able to show that this is equal to u of minus n plus 3, but we have been asked to write it in the form u of mn minus n naught. Okay, no problem, just compare these two. Okay, compare, this is A, this is B. Okay, comparing A and B, the arguments of A and B. Then what do you get? M is equal to minus 1. That's the time reversal, right? That is what is producing for you the time reversal. And what is N naught? N naught, don't make a mistake, as plus 3, basically in order to get this particular expression, N naught has to be minus 3, because minus of minus 3 will give you a plus 3. Then if you substitute these two values, then u of mn minus n naught will be the same as u of minus n plus 3, and that is the sequence that we are interested in. So again, the concepts that in terms of time reversal, how to sketch the sequences, when you take the difference of two sequences, all of those things come into play, and we want you to be very, very comfortable and confident of the material that we have covered so far. So with that, let us look at some of the one more concept that we had looked at previously, that was the aspect of causality. Now we said that a discrete time system is causal if the output at a time instant depends only on the input at that time instant or past inputs. It should not be dependent on future inputs. And we also said that if it was an LTI system, this would be characterized by an impulse response, and the discrete time system, which is LTI, would be causal if the LTI system's impulse response is also causal. So we can check either using the general definition, or if we are given that it is an LTI system, then we can check for the causality in this fashion. Okay, so I just want you to think of that, and hopefully you are comfortable with that. So the aspects of causality, that is what we want to check, and be able to expand and explain what these examples are. So what I would like you to do is to look at the examples that we are going to be looking at, and quickly tell whether these signals would be causal or not. All right. So let us take a quick look at the first example of a causal system that we are want to check. Right. Example: y of n equal to x of minus n. Example 1. Okay, this is a discrete time system. So basically, it's a system that does a time reversal. So if I put input x of n to this discrete time system. Okay, this is the discrete time system. Output comes out to be y of n equal to x of minus n. We are asked to check if the system is causal. So, we will always say, okay, y of 0 is x of 0, causal, no issues. Y of 1 is equal to x of minus 1. Okay, this also is causal, it is a past sample. Y of 2 is x of minus 2. And we say, okay, I have checked causal. No, you need to also check negative values, right? What is y of minus 1? It comes out to be x of 1. So, at time minus 1, the output depends on the input which is in the future with relative to that input at minus 1. So, once you take this into account, this also, then this system is not causal. It does not satisfy the properties of a causal system. Okay? And it turns out that this is not an LTI system, and therefore it does not have an impulse response. So, we can't use the impulse response criteria, you would have to actually expand it out. So, the answer to the question is this system is not causal. Example 2, y of n is equal to x of n cosine of n plus 1. Okay, you may say, well, wait a minute, I can already see y of 0 is equal to x of 0 times cosine of 1. Okay, it's a future value, so it's not. No, wait. What is the definition of the system of the causality? Output must depend on the input at that current instant of time. Okay, this is not the. This is a scale factor. Scale factor that is multiplying the input, but actually the input is this one, x of n. Okay, output depends on input. So, is this a causal system? Y of 0 depends on x of 0 times some scale factor. Y of 1 is x of 1 times the scale factor. Y of minus 1 is x of minus 1 times scale factor. So, therefore, this system will be causal. Okay, because the output depends on the input at that instant of time and some scale factor. It does not matter what the scale factor is. You just, so, if the sort of the non-causal looking term comes in the scale factor, don't get fooled by it. That is not going to affect your decision. You are going to have to you should declare it as a causal system because it satisfies the condition for causality.